now that we've gotten past the very, very basics part, that is technically chapter 1, all we're going to do with chapter 1 in your physics book, only because I want to make sure that the rest of the course is going to be done with the same philosophy that I had for the previous 2 classes we had. I'm a firm believer that my process is the easiest one to do the complicated problems. Not saying that the complicated problems are going to become easy, but I'm saying that you make it easier by having a process that you don't have to worry if you got the right process or not. If the bottom line to yesterday is that if you make everything cancel out label-wise, then you're probably right. I think I might have told you this before, but very quickly I'll tell you this. I took a magnetism class for my master's at Eastern Illinois University, and I was so lost. Nothing makes sense. The formulas didn't have any concept of reality in my mind. I did not see how it fit, but when I did the problems, we had these formulas, and we had a ton of constants that we had to plug in, and I figured out that if I get my constant in there, I looked at the labels of the constant, if I made everything else fit, as far as canceling it, I'm going to end up with the label of the value that they were asking for in the test. I got it. So I took this test that I was so sure I was going to fail, and I got 100. I have no idea what I did. I don't understand what I was solving for, but I knew what the answer was supposed to be in terms of labels, and that got me through. So keep that in mind. Okay, so this topic and the next topic kind of dovetail into each other. A lot of people get them confused. It's pretty common because most people are not into the whole science thing, and so they don't understand that there is a nuance involved, and nuance is a very important aspect of solving problems. Because if you get into your head that things should be a certain way and you ignore everything else around it, you're probably not going to solve the problem. But the nuance, the little differences that make a huge difference in the overall process becomes real important. So like in this case we're talking about speed, and tomorrow we're going to talk about velocity. In this case we're going to talk about distance, and tomorrow we're going to talk about displacement. People think speed and velocity are the same thing. They are not. They are based upon, the velocity is based upon the speed, but the speed is not based upon the velocity, as you'll see. It's like, what's the expression I'm looking for here? Suppose that somebody comes up and says, well, that's enough about a theory. They don't know what the heck they're talking about. What they're talking about in actuality is that it's just a hypothesis. You know, in the scientific method, you state a question as to what problem you want to solve. You have a guess as to what that is. That guess is called a hypothesis. A theory is a proven statement. But non-scientists get those two messed up. I see a lot of reporters and pundits talk about, oh, it's just a theory. No, if it's a theory, it's probably true. If it's a hypothesis, it's a guess. So I really wish they would say things more truthful, but that's not going to happen. You know, it's the same like people who like to sound intelligent and say, well, between you and I, no, I is not a subjective noun. It is it's not an objective noun, pronoun. It is a subjective, and therefore it should be between you and me. So people get these things wrong all the time and take it as a fact that that's the way it is. And you've got to be careful with that. You've got to be your own person. You've got to know what the rules are, but you also got to know how to work around the rules. Work with the rules, create new stuff. That's what you're going to do. Okay? Speed is a scalar concept. Now, a scalar concept deals with only numerical values. That's it. Okay? Meaning that is defined without any context to the surroundings. That's a great way of putting it. No context to its surroundings. It just is what it is, as somebody famously said. If I say I've driven my car 50 miles, that is a scalar quantity. If I say I've driven my cars 50 miles northwest from my house, I have now given it context. It is no longer scalar, it is now what we call a vector, which we will talk about in the next discussion. In the past, you have been taught that speed is defined as being the distance divided by time, or s equals d over t. That is true. But again, you will notice no context is given to this. So as I said at the beginning, it is a scalar quantity. In order to calculate an average speed over a long distance, then this becomes the total distance divided by the total time traveled. All right? Now, get your books out and take a look at page 60, problem number 1. This brings up a geometry concept that you will often have to recall, like so many others. The problem asks for the displacement, which we will talk about tomorrow. But let's just deal with the distance. Let's calculate the distance a car travels in half a lap of a circular track that has a radius of 150 meters. So what I'm going to do here, even though I've got it written out here, I'm going to put it in a mathematical format here. So we've got 150 meter track, our radius of a track. Okay, in order, and this is a calculated distance car travels in half a lap of a circular track. So we're going to go half a lap. And so what is the distance that this is going to be? Well, the distance the car is going to travel, and this is a circular track. That's kind of important. It goes an oval or an elliptical path, that takes a whole lot more calculating. But we could do it. I don't want to do it. But we could do it. So we're just going to look at a half lap. Now, what is a lap? What does that mean, lap? Half a lap? Well, what is one lap of a circle called? Circumference. Right? What is half a lap then going to be? It's going to be the circumference divided by 2. So here's where the geometric formula comes in that I've asked you to be cognizant of, having your little toolbox if you can't remember. Little story again, I'm good with these stories. When I was a kid, I was helped raised by my grandmother, sweet lady, loved her to death. And she was always cooking for me. Now, when I graduated from high school, I weighed 132 pounds. So my grandmother tried to fill me up because we didn't eat a whole lot. My dad was a minister, we couldn't afford a whole lot of food. And when she showed up, she started buying us food, and I never fattened up because I played sports all the time. But she used to make me apple crisp. And she, apple crisp was, she made this in a square porcelain dish, this deep dish apple crisp. Oh man, I love that stuff. Oh, she also made me cherry pie a lot, because cherry pie was my favorite kind of pie. It's also my favorite kind of cake. It's kind of a weird kid, but I was. She made that in a round, of course, like a pie pan. It was really deep. It was almost like a cherry cobbler, but it was a pie. She had the crust over it. So when I learned these geometric formulas in junior high, living in Babbitt, Minnesota, up north of just by the Canadian border, I had to figure out a way to remember these formulas because we had to memorize these geometric formulas really early on in my life. So I used to call apple crisp apple pie, because I'm an idiot back then, still am. So I would say apple pie R squared. And then the cherry pie is D. How about that? Huh? Clever kid, wasn't I? Yeah, nobody liked me.